To continue, we have to Professor Diego Souza introducing to Professor Claudia SagastizábalTitulada. You can start, Diego.
Okay, so thank you very much, Juan. So it's a great pleasure to have Professor Claudia SagastizábalTitulada here in our webinar. Professor Claudia is professor at UNICAMP, Universidad de Campinas, in Brazil. She's an applied mathematician working on convex optimization. She's has received she has been invited to very important congress, international congress, and she have around 100 papers and 2,000 citations. And today she's going to talk about revisiting operator splitting method. So, Professor, thank you very much. So you have the word.
Okay, thank you. Good afternoon or good evening. Or hello, everybody. Thank you for the invitation. I will talk today about the topic. My area of expertise is numerical optimization, variational analysis related to optimization. And since this is a public that is focusing especially in EDPs, in PDEs, then I thought that, well, maybe this topic would be of interest. It's about, as the image there shows, I gathered all the, I made a picture of all the scissors that I had at home. It's about how to separate problems that are too difficult, but nevertheless exhibit some particular structure that makes it that some of the terms separately are easier to solve. And this is what is an idea, I don't know, maybe it's divide to conquer idea is very fruitful in many areas. And so my particular interest, I am a researcher I'm not professor in Campinas. In fact, I live in Rio de Janeiro. I am collaborating at distance and associated with UNICAMP, and I'm associated with this CMI, that is a consortium of universities in the state of Sao Paulo that tries to integrate the mathematics, industrial mathematics with the industry, get it closer and help traversing what is called the Death Valley, to all the innovation that we have in the universities, try to get it into the industry, to the productive sector. So, and this is a very nice center that is founded by FAPESP, and has really done important work in this area. It is, for example, thanks to different activities of this group, the last couple of years already, I have seen PhD students in mathematics that went to work, that are working in different institutions that do not usually hire mathematicians, but that realize that this is important. Applied mathematics can give them some edge. This is well, the research center of Eletrobras, also the chamber of electric, the trading, energy trading. So because my applications are mostly in the energy sector. So this is the interest of this type of activity. And well, now my talk then starts with the motivation. Why is it that I'm doing what I will talk about? It's because Brazil is a continental-sized country that is very green and sustainable regarding production of electricity, because most of it, as it can be seen here from the color of this map, is blue or green. The dark ones are the fossil fueled sources of energy, and the blue one in particular makes it very clear why it is, what is the importance from an economic point of view, an ecological point of view, of course, too, but from an economic point of view, of the water. The water for Brazil, it's a very important resource. It is the combustible that generates most of our energy. You can see here, it's, let me see, I will make it bigger for me because otherwise I don't see well. I didn't put my glasses, but well, it's more than 50% only from water. It is a very important source of energy. But water has a problem. Water does not have a cost, right? How do we, the gas price or the oil price for the thermal power plants, even the nuclear pellets that are used for nuclear generating energy in the nuclear power plants have a price, a cost, a market, and then how much it will cost to produce that energy is known. But from water, the situation is different. And especially considering that decisions that we take in the present time have an impact that is important in the future, and that has to be taken into account, but the consequences of our current decisions in the future will depend on how much water we'll have in the reservoirs in the future. And this is not controllable, right? It depends on the rain, on weather conditions, on the climate. So today we can decide we will be saving money, then today we will not spend, then we will not dispatch or turn on a thermal power plant, or many thermal power plants, because like this we will not spend money burning fuels today, and we will just let the water go through the turbines in the dams where we have reservoirs, and then this water is free, so it will be cheaper. So we will be aiming at minimizing our immediate cost. This decision today, in the future, because we want to keep on doing that for the days and the years to come, have consequences. And well, if it rains in the future, then the decision of using our resource today will be okay, while if it doesn't rain, we will have deficit, and maybe we'll have to turn on some very expensive fossil fuel power plant. I'm not talking even here about the sustainability or carbon emissions or anything. It's just in terms of money-wise here. The other considerations are also important. But the problem here is, what is the value of the water for this business? Then if we, on the other side, we say, no, I don't want to minimize cost today because I'm scared of what will happen in the future, and we become conservative today, and we keep water, we will accept to spend more money by generating in the thermal power plants the energy. That means that we will have to burn fuel, and then this will increase the cost of the energy and the price that we will all be paying. Okay, and so if today we are more conservative, then in the future this has a consequence, because again, if it rains, then we kept water for nothing. We will have excess water, maybe not to flood the villages around the dam. We will have to release water without generating energy, because we will have more than the capacity that the turbines can take. And this is a waste. It's a waste of a valuable resource. And on the other hand, if we were conservative today and tomorrow it doesn't rain, this will be a good decision. So there is always this trade-off that needs to be found in a business that is very important for the country, and well, in general, for all the countries. Energy is strategic for the growth of a country. And then from the mathematical point of view, the value of the water is in fact the opportunity on the substitution cost. How expensive it will be if in the future, because of decisions today, we have to use fossil fuels. And this is, in mathematical terms, this is the value function of an optimization problem. Since there is randomness, the uncertainty of the rain, the inflows, the water inflows is a technical term, this will be a stochastic programming problem. It is a linear stochastic programming problem because it is gigantic. It has an astronomical size. I will give some idea later, because it depends on the reservoir volumes in the whole of Brazil, on how we represent uncertainty, how the uncertainty is handled in the optimization problem. If we consider that, for example, every month we know if it rained or it didn't rain in some region, and this changes the estimation we have for the future. This is a way, for example, of handle uncertainty. Is the one that is being used. It's a multi-stage stochastic programming problem. It's called in optimization. It depends on how we try to solve these gigantic, very large size optimization problems. It depends on environmental constraints. For example, those that I mentioned, we cannot release too much water because we may flood. Well, I didn't mention. I mentioned the ones that we can flood the dam where the water is kept. But if we are in a hydro valley, it's called along a hydrographical basin, usually we have a power plant upstream, then this one generates energy, then releases water and fills the reservoir downstream that then has combustible, it has and then it can generate water. But if we release too much water, we may flood the dam, the downstream. Also, there are constraints that are imposed by the Agencia Nacional de Aguas, the water national agency, that says it's fundamental for the economic life of, for example, San Francisco River, that is very important here in Brazil, to ensure navigability or to make sure that there will be sufficient water for agricultural use or for cows or for human consumption. So there are all those considerations that have to be taken into account when solving this very large optimization problem, whose value function gives this estimation of what is the value of water. And as I said, it has economic impacts. The social impact is also very important because there are more than 400 agents in the energy sector in Brazil. And there are a lot of rivers. Here it's a schematic diagram. In the bottom here we have the Atlantic Ocean and the hydro basins. Dots means that there is a power plant that doesn't keep water, just when the water passes through, then it generates electricity. A triangle is we have a dam, and while we have a lot of very large, there are reservoirs whose surface in Brazil, whose surface is like the same surface than the country of Luxembourg. It's not a big country, but for a reservoir, it's a big one. And then the water takes many days to get from the upstream water plant until it goes into the ocean. And so there are a lot of couplings, and you see there are some basins also that are interconnected. Sometimes there is water that is pumped upstream so that you make sure that there will be water when you will need it most at peak times, when the demand increases. Now, there are a lot of complications, it's a large system. And because of the geographical spread of the country, the climatic conditions, the amount of water that each reservoir will get is different according to the different regions that are divided in four for this purpose. So, as I said, the future cost of water is a piecewise linear function. Here it depends, then x0 is the state of the reservoirs. I separated them, my variables, in control variables and state variables. The state variables are how much water we have in each reservoir, because it tells us if the system is wet, then we are well, it's abundance. If there has been a lot of drought, then now the system, well, it will be more difficult to satisfy the very important constraint that is here, the demand. Okay, we have to at least, there is not important here to enter into the details, except to say the BAL equation is just, it tells us the water, the volume that we have, this X, the state of the reservoir, how it changes when we generate energy, or where sometimes we have to spill some water because the turbines do not have enough capacity, and if it has rain or there is evaporation. So it is what is called the hydro balance equation. We have state and control variables that are in a box. And then because the rain is unknown, it's not even the rain, it's how much water it will arrive into the reservoir. Because if the past months have been dry, then the water, the ground, the earth will be thirsty, and then it will absorb a lot of water, and not much will arrive into the reservoir. So that's why we speak about water inflows. And because of this red data, we have to consider an expected value, or an integral if you want in continuous time, but here we have to discretize everything. This is in fact the discretization of differential equation. Okay, so this problem, what is the size that I said it's big? The regions we are identifying like 4 different regions in Brazil: north, east, southeast, and center, west, and the south. These are the 4 separate regions that are defined like all those hydro basins that you saw are converted into some equivalent reservoir that tells us what is the state of this geographical region. Okay, something that I did not say is that those reservoirs, the Q equivalents, are so large and there is so much water wells in Brazil that there is something very important that tells what is the horizon, the time horizon, what is T, capital T, that we have to consider here. It refers to how long it takes to empty the reservoirs until complete depletion of the reservoir. Well, those equivalent reservoirs, and this is called regularization capacity, those equivalent reservoirs in Brazil have a capacity of several years. It would take more than 3 years to empty complete reservoirs. This means that to look at the cycle, we have to aim at an horizon of at least 5 years, right? Discretize month by month. But the situation is even worse. Is that since we don't give, you see, we're here thinking only of the thermal generation, how much we will spend in generating thermal power plant, and this is what will give us this substitution cost. This means that any model of optimization, because it has a finite time, at the end of the horizon, will end up with the empty reservoirs. It's natural, it's optimization, so it's cheaper to use the resource that costs less. And because of that, we have to consider an horizon that is double in time, because this perturbs all the, we call it the end of the world or a phenomenon. This affects all the decisions, and then so to be able to take with confidence decisions for the first 5 years, we need to consider 10 years. That means monthly discretization, 120 steps in our variables for each of the reservoirs. And the thing gets even more difficult because of all this uncertainty. It means that, for example, here, this is a very small scenario tree that says, well, today we're here, tomorrow it may rain more, rain as usual, rain less, and so on and so on and so on. Each month opens a fan of possibilities. And if we only consider 3 hydro conditions for each month, which is not much, then in 4 months, we will have 3 to the power 3 scenarios. And scenarios means that each one of those variables will have to be replicated because it will be different, the decision that we take according to what happened, right, regarding the rain. So you start to see what is the size. And the people who work with hydrology in Brazil, after a lot of studies, decided that for 3 scenarios is very little. In fact, we need to take 20 scenarios, 20 scenarios, open 20 possibilities in each node. And this means that we have to deal with this kind of number of, not number of variables, of different possibilities for each variable involved in our decision problem, 20 to 119. Okay, so you see that, well, this is just not possible to solve. There are methods that are sampling methods where instead of looking at all the scenarios, you randomly draw some scenario, and well, that helps approximating our holy grail, that is the value of the water. Because, and I didn't say, the value of the water, how much it, all that is to know how much it will cost the value of the water in the first month, so that for the next month. And for that, we have to look at the next 10 years. And once we know how much costs the water for the next month, we will be able to decide for the next, for the weeks of the next month. And then that will give us the value of the water at the beginning of the next month, for the first week. And this will be used to define how to generate water, how to generate energy for tomorrow. And this will give the cost of electricity that eventually impacts in the price. Okay, so it's to give value to this asset that is has no cost, and then it's difficult to evaluate and to price. And it is a very complex and very interesting mathematical sequence of mathematical optimization problem. Okay, so we need to decompose. This is why the scissors in the beginning and why the scissors in the end. And then now that I have, and well, of course, this is done for the next day, that this kind of calculation that I said that every day is being run by the independent system operator, and in Brazil the name is Operador Nacional de Sistema, ONS. They do this in parallel computations because it has to be done in 1 hour for the next day. You get all the data of which power plants are working, which are not, what is the state of the system, how much water we have in the reservoirs. For the next day, you can consider that you know if it will rain or it will not rain. There is not stochasticity there. But then the problem is very big because we are not aggregating equivalent reservoirs or anything. It's very individualized. Even different turbines in each hydropower plant are considered, if they're on or off, and then there are zero variables. It's a very challenging problem too. So it's done with using parallel computation. So we are interested in being able to study the composition methods that give a sequence of, instead of solving the big problem that we cannot, we will define a sequence of problems that are easier to solve and that asymptotically will give us a solution. It's from 2016, and it's people from numerical analysis, from optimization, from EDP, PDEs, that decided to put together works that are from different areas, but eventually are doing very similar things, and they are related to splitting methods, to operator splitting techniques, which is what I said in the beginning, trying to separate difficulties and defining subproblems that are easier, and then sequentially, asymptotically, try to solve the problem that, as in my example, my motivation, it's untractable. And it has then contributions from PD scientific computing, from information sciences, from optimization. Okay, so splitting is not new. I put here some milestones. There are more, but it goes as far away as 1875, when Sophus Lee, the one of the Lee brackets, he defined a constructive scheme for a dynamical system of this form. So we have the derivative, then we have the sum of two linear operators. This is this. Then, of course, at this time, Lee was not trying to make a numerical approach. It was to try to show the solution of find the solution, prove existence for this linear dynamical system with this particular structure. And then the idea was then to consider a subproblem that involves only A1 and another that involves only A2, then somehow coordinating this information and defining another iterate. Well, then there were almost 100 years that passed, and it came This technique was extended by Rashford, Pisman Rashford, and then Douglas Rashford. There are several works that with Rashford as a co-author, where it moved from linear to nonlinear system. This is possible. So, for example, the structure of the two problems makes it that making a backward step for A1 and a forward step for A2 is easy. And then we exploit this by defining separate problems that have some relation with our sum here, and then, well, they are coordinated so that eventually we get the solution that of the sum, right? So there is also then Douglas Rashford that, as I mentioned, then we have in the 70s, end of the 70s, the French school came into the game, and considering, instead of equations, generalized equations, inclusions. We have here multi-valued equations, operators, but the sum of two operators, right? So you see the degree of generality becomes higher and higher. And then there are the works of Lyons and Mercier, then Gadet, Globensky, Marocco, Letalec, and the very well-known, I don't know, at least in our area or in machine learning, in optimization of machine learning, alternating direction methods of multipliers, ADMM, is part of this family. Okay, then in the 90s, there was a unified analysis considering those operators, maximal monotone operators, and then, well, there is extent, there is also works by Rockefeller, and they're all based on the proximal point algorithm, Bersekas, Nesterov. Well, then the more people kept on working, and in 2016 there was an explosion. A lot of works on mostly because of the interest of these kind of approaches, the composition methods based on proximal point theory. So always exploiting A1 and A2, exploiting this fact. Then in machine learning and in image processing. This I think explains many works. Well, there are just some, so they can be used in distributed optimization, statistical learning, or there's a cloud. Okay, so the idea is that you want to solve an inclusion of that type. You want to find an X such that 0 is in the image of an operator A that is the sum of two operators. Okay. When this resembles a little bit to Newton's method, right? Newton's method is a method to find the 0 of the root of a nonlinear equation, capital F of X equal to 0. Now, in many of those problems, in distributed optimization and statistical learning, the operator A is not anything. It is not any maximal monotone operator. It is the subdifferential of a function. So the same done when we pass from the general Newton's method for nonlinear equations to the Newton method in optimization, where we know that the nonlinear equation corresponds to 0 and a gradient of a function. The question is, can we exploit further the fact that those methods that I mentioned did not do this decomposition? Douglas Rashford, the composition methods did not do. They stayed with as if it was the sum of two subdifferentials here, but without paying attention to the fact that there was a function behind this. So can we exploit further? And why this is important? This is important because let me just make some digression here. Why in Newton's method that we all know, it was interesting to introduce the knowledge that was by the end of the 1980s in optimization, the knowledge that the nonlinear system that we are solving corresponds to the gradient of a function. So, well, capital G, sorry, the nonlinear system that we solve by Newton is just to make a first order Taylor expansion around the current iterate, and we get fast convergence if we are sufficiently close by simply solving the linear system defined by this Taylor expansion, centered at the current iterate xk. And well, this we all know. This instead then of finding the root of this, the zero of this blue curve, we will find progressively the zeros of affine lines of this type until, well, if we start close enough, we will converge. So this is the original Newton method for nonlinear equations. And the big advantage is that we say that it is fast because it has a quadratic speed of convergence, but in fact, what it is that it's accurate. Here we have an implementation for this function of Newton method, and then in red you see the number of digits of accuracy that we gain at each iteration. So 1, 1, 1, then 2, 5, 9, 15. So it is precise, it is accurate, Newton methods, and this is something that we like. Now, if it is for optimization, this Newton method, the capital G here and the G prime, the Jacobian, in fact, are the if the G is a gradient, the Jacobian will be a Hessian, right? If we are trying to minimize a function, and instead of minimizing the function, we want to solve the optimality condition, Fermat condition, 0 is equal to the gradient. So the difference, we replace everywhere G by the gradient and G prime by the Hessian. And so this is the solution for an objective function. But now, if we remember that we want to minimize a function, we can interpret this iteration of Newton method for in an optimization form as, in fact, we're minimizing a model of the function. And the model that we're minimizing, it's a Taylor expansion of second order, because it's for the function, no more for the gradient, and around the current iterate. So we're trying, instead, at each iteration, instead of minimizing our function, we minimize this model. Okay. So if we now think about the function that we're minimizing when we're solving this model, this function, this nonlinear equation that I showed in the beginning, we have to minimize this function. And then the model is first this one. It's a quadratic model that will be approximating our function locally around the current iterate. Now, everybody knows that a weakness of the Newton method for optimization, when it is written like this, is that we have to compute the Hessian. And this is heavy computation. And the question is, can we avoid to compute the Hessian? And the answer is yes. Instead of computing the Hessian, we will, in our model function, we realize that the only thing that matters is that this curvature that gives us the second order information in the model is important only asymptotically along the directions we are generating. And this gave rise to the quasi-Newton methods in optimization and the conditions for achieving speed that is not as fast or as accurate as Newton, a pure Newton, but it is satisfactorily fast too. So we will be solving this type of linear systems with M will be a matrix that has special structure where we can take advantage of sparsity perhaps and things. So it's not like the Hessian, it's much easier to compute. And then it's easier to solve these systems. Okay, and then, well, just to compare what will be the difference, it's a little difference in the model function that we're minimizing at each iteration. And if we compare the precision, the accuracy, we see that, well, Newton, well, was more accurate here on the right, but on the left is not that bad. Here is the number of digits that we are identifying at each iteration for the very same example. So this is the end of this digression, this is the tour that I wrote in French here, and it tells us that exploiting structure can help. Knowing putting into the solution of your problem all the knowledge that you have available can help. For the splitting techniques that I was mentioning, when you want to minimize a function that is given by the sum of two terms where you have this dependence, for example, in the variables, Then if you write the optimality conditions, you will get your operator A and your operator A1 and A2. And then the idea is to find a sequence of iterates where you just define a case of problem on this subdifferential and another subproblem on using only the second subdifferential. Well, you can also think of the dual. It will involve the conjugate functions there. It's more or less the same. It just depends on what is more, it's easier to do. For example, if you have a sum of functions, like we had there in the objective function of our water value problem, it was the sum of cost of generation, then and you have equation, you have some relations that couple the decisions. For example, you will generate as much as to satisfy the demand, right? So then you can make write a Lagrangian to make the case of problem easy, because a priori this doesn't fit the structure separation. But if you introduce dual variables, this can be done. And then the Lagrangian, if now we have a sum of terms of objective functions, each one depending on the variables, and then you have these constraints, then you introduce a Lagrangian multiplier W. And since the coupling constraint is relaxed in by the Lagrangian, then this gives rise to separable Lagrangians. And this is what is good in for this type of approaches. Then you will have a primal step where, having a dual iterate, you will solve all those separated Lagrangians. You will find xs, x1 or x2 here. I put s because later on it will be convenient, by indifferent, and this is that I was mentioning in parallel. And then having this primal information, you use it to make an update of the dual variable of the WK. So Lagrangian relaxation is very good for this type of structure, and it has been exploited a lot. For example, something that is very well known in distributed learning or machine learning, you have compressed sensing. You want to minimize the distance, some error, some quadratic error, that depends. So this is your model and these are your measures. And then you don't want to use too many, to have too many non-zero terms, and then they add this norm one term, or it could be total variation if you are more used to that, but usually it's used norm one, that will result in parsimony. Not many non-zero variables for x1, and this is something interesting because the models that will represent for all these classifications and how Google or ChatGPT is working are based on these type of things. You don't want too complicated models, so less terms for the model, and this means less non-zeros, less non-zero components in the decision vector here x1. So, but here we don't have this separability. You can think, but this is what you do. You lift the problem. You define an additional variable x2. You see here we had on the second term here a1 x1. Define an additional variable, and then you say this additional variable has to be equal to what was here, right? And then like this you have f2 and f1, depending only on x1 and only on x2, and you can put the machine here in place by introducing a dual variable that will deal with this coupling. But what is interesting here is that this coupling is very special. This is a subspace. It's a very simple subspace because now we're thinking instead of an x1 variable, we now have the spaces x1, x2, and this is a subspace where it is, for example, very easy to project. And because of that, all this splitting where you solve different problem on x1 and a problem on x2, I said that they have to be coordinated. The coordination will be to project into those subspaces, and this will be easy. A more complicated, evolved example is that illustrates this phenomenon is called the progressive hedging algorithm by Rockefeller and Wetz, that allows to solve stochastic optimization problems like the one that I solved in the beginning, where you have an expected value that depends on the scenarios. Remember how much it rains, and then decisions we take, decisions that depend on the scenarios, and you have to parse a scenario tree. Yes, then here is a scenario. So if you want, you can write here with the probability. And in fact, this scenario tree and this, by the same token that of lifting, repeating, making copies of variables, and then saying the variables have to be all the same, can be written also as an optimization problem in an augmented decision space, but where the variables are coupled by a simple subspace. And then I will explain this in a graphical manner. Suppose we have this very simple scenario tree, then we have here the probability of each scenario. A scenario is a path from the beginning until the end of the tree. It were okay, it rained a lot, it didn't rain, and so on. And these are called the stages, will be the first month, second month, third month, and so on. Okay, so how is it that you do this rewriting? You make copies of the variables. This means that for the first scenario, we have 1, then 2, and then we have copies, okay? And then, so we will repeat, we will have variables with indices given by the scenarios. And then you have to introduce a constraint that will couple what has to be coupled. And here the colors are telling you what has to be coupled. So the first component of all those variables has to be the same, because the decision has to be the same in all the situations. Here we have all those 3 copies. The decision on the second variable here has to be the same. Well, and then you write it like this, then here you write it like this, and then the other color, and then this defines your space of is called of non-anticipativity. And it's a very simple subspace where it is easy to project. Okay, so now that we have our problem written in this larger dimensional space, we say, okay, what happens if we do our Lagrangian relaxation approach? Well, there is some other approach that is called and this is what we already wrote. I repeated it here. The Lagrangian relaxation is very good because it induces separability, but the disadvantage is that you may end up with a solution, a point X that does not satisfy or that is not a solution of the original problem unless you are sufficiently convex. So if there is some lack of convexity in your problem, you will end up solving a convexification of the original problem when you want to solve the original problem. For example, if we have 0, 1 variables that mean we turn on or turn off a power plant, the Lagrangian relaxation will end up telling you turn on half of the power plant, because it doesn't work with these 0, 1 variables. And all this is not something that is useful in all the contexts. In some cases, you need exactness and feasibility, primary feasibility, and this is brought into the Lagrangian scheme by what are the augmented Lagrangians. So the augmented Lagrangians, what do they do? To the Lagrangian that we have, they add a term that penalizes the constraint violation with a quadratic term here. So this is good because then it forces a sufficiently large penalty T0 augmentation parameter, then this constraint will be satisfied, and then you will get a 0 or a 1, for example, turn on and off one power plant. That if you want to keep your scheme where you have separability and we were solving in parallel the difference of problems that were associated with the variable, the decision variable xs, in each scenario, because of this quadratic term, there are the cross terms there in the quadratic when we expand the square, that we lose the separability. So augmented Lagrangians, it's very moral. This you win on one side, you lose on the other. it do not give you separability. And then what do you do? You think of this Newton idea going to quasi-Newton. We will make a model, a local model of this augmented Lagrangian that is separable. And instead of solving primal problems that are exact, we will solve approximate primal problems. This approximation has to be handled with care, but it's something that can be done. Let me see it. So what we will do is, then we'll start with a primal point that repeated then in all the variables, a dual variable that will be in the orthogonal complement of this subspace. This is just by duality. And then we will solve separately these approximated problems, where the augmented Lagrangian, where we will fix, for example, see here, here, we separate the S variable from the non-S, no, from the others, and then we fix at the case iteration the other variables, and we solve in the current variable, and then we obtain this value, and we use it in the next, or if we do it in parallel, we use it at the next iteration. So this is what this means. K minus S, it means all the variables that compose our big decision variable with copies, we fix them, except for the current that we are minimizing, not, and we do this in parallel. So, and then to put all together, we will project. So this set of copies we will project to get the new iterate, and then, well, we will define a new dual variable, and we will continue. So the convergence, this is the Douglas-Rushford operator splitting algorithm that I'm explaining it, but applied here in this context of stochastic linear stochastic program. And a disadvantage of this of these techniques is that this augmentation parameter of the augmented Lagrangian that is being approximated at each iteration remains fixed. And if you see from where it comes, we are trying then to minimize our objective function, and we are trying to satisfy feasibility, to ensure feasibility. And with a fix, it's like if you had a multi-objective of the objective function here, and with a fixed parameter. And this is impairs convergence, because maybe in the beginning you can accept to be infeasible, more infeasibility, and then T0 will be small, and you want to get close to where the decision variables are close to the optimum, and there you will be worried about satisfying your constraints. You want to be able to move those variables. And here you see what happens. It is very well known, it is a weakness of this type of problems, that you have to hit the right value of this augmentation parameter, because you cannot change it. For the same problem here, lower means more accurate. Is it minus the number of digits that we have for this? It's a two-stage, a sequence of two-stage problems. Then if you start with T0 equal 1, you don't improve anything. Your accuracy, initial accuracy, a little bit, T0 equal 10, and if you put just by divine inspiration, this 100 jackpot, you get a very good progress. So this is because nowhere we exploited the knowledge that we know that we're minimizing a function. I explained it like we're minimizing a function, but the method was derived thinking 0 belongs to the subdifferential of to the sum of two operators. So if we interpret the primal and update in terms of the dual problem, here is where the optimization comes. A question to the organizer, I'm running out of time, probably. How much time do I have? I don't hear. Well, I will assume that I have 5 more minutes. So if we interpret then the primal update in terms of the dual problem, we see that when we are doing this iteration that is being done by this Douglas-Rushford splitting method, in fact, is trying to solve a dual problem that is separable and whose dual variable is in the orthogonal of the original subspace. And this is done by computing proximal point methods. So once we know that, we are able to compare the value of the dual variable with the value of the model. Before we did not have this tool. And if we do that, then we will be able to let this argumentation parameter vary. So since we are seeing with dual glasses our optimization problem, then we'll first compute the dual problem, the dual variable. Remember that before we were computing a primal variable in parallel, and then we were projecting and then computing the dual variable. Here now we will compute the dual variables in parallel. We will project the dual variables, and then we will update the primal iterate. They are equivalent when the problem is convex. And then because but now the big difference is because we have, are wearing these glasses that are dual, we have the possibility of checking how good is our dual model with the dual function. We can check if there is consistency there. If the fit is bad, then we will decrease the parameter, augmentation parameter. If it is good, we can increase it. And then this allows us to move. This is something that in bundle methods, for those who know non-smooth optimization, is called a serious a null step. The fit is bad, it's a null step. The fit is good, it's a serious step. Okay, for those who want to know how is the theory that where we can show then for this type of methods, asymptotic convergence, global convergence, and starting them from any point and allowing to vary in a reasonable manner these augmentation parameters. Here are as long as they are long iterations, we keep bounded this parameter. Then we show global convergence with a linear rate, which is not bad because we are not knowing much here. We don't have second order information or approximations of second order information because the dual function is non-smooth. In general, non-smooth methods have sublinear rate of convergence, and here we have linear, which is good. It's fast. And if we have an infinite sequence of the bad fit problems, then what will happen is that we will be converging to the last iterate of the last serious iterate, the one that was good, and this will be a solution of our problem. So, and we have an implemented stopping test, and just to see the difference, this here in red, we have what happens if we run the original problem that the Douglas-Rushford splitting method, the progressive hedging method in stochastic programming with T0 equal 1. If we run it here with T0 equal 1, but using this approach that I presented, that we call it bundle progressive hedging, then of course, since this one could not change because the conversion theory doesn't permit to change the parameter, so it keeps the same. But in our approach, we can change it and adjust it along iterations, and of course, you see the performance for the 3 different initial values of this augmentation parameter is much less important. This was the one when we were hitting the jackpot, and here we have that it's almost indistinguishable. It doesn't matter what is the augmentation parameter. There is not divine inspiration that has to come to try to guess what is the good one, because we can make a wrong guess, initial guess, but then along iterations we will adjust and then we will converge. Okay, so this is my last slide, and just related references is a paper that is appearing, I think already, it appeared already in SciOpt, and another one that will be appear in Journal of Complex Analysis. Okay, so and this is the end of my talk. Thank you, and sorry for the coughing.
Okay, thank you very much, Professor Claudia. So now we open the turn for questions or comments. So if anyone has some question.
I have a question, Claudia. Could this problem be looked as from the point of view of dynamic programming, or it's just completely nonsense?
No, it's not nonsense. You mean the
decision tree and
yeah, well, in fact, the way of solving this sampling method that I mentioned is the technique that is used worldwide in the energy sector, because they have to deal with these big problems. Is called stochastic dynamic dual programming.
Okay.
Where you don't, in dynamic programming, you discretize all the state variables and start interpolating. Here, you let the optimization process guide you through which states you will be using for your approximations.
So if it's somehow related, do you have problem with the curse of dimensionality somehow? I mean, or the splitting solves this?
The splitting is an attempt to solve this the dimensionality curve.
Okay, thanks.
Okay. Any other question or comment? So if not, let us thanks again, Professor Claudia, for this very nice talk. Okay. So I give the word to Juan to end the session.
Thank you, Diego. Thank you a lot, Professor Claudia Sagastizábal, for your amazing talk.
Okay. Thank you.